Welcome to the deep dive. Today we're tackling something pretty substantial. The core ideas of physical and inorganic chemistry, specifically at the AS level.
That's right. Think of this as a way to really get those foundational concepts without getting totally bogged down.
Exactly. Our mission really is to pull out the absolute essentials from, well, a whole load of learning outcomes and notes. We're covering 22 key areas.
Yeah, it's quite a list.
We want to give you those aha moments, We're going through atomic structure, bonding, energy changes, equilibrium, right up to an intro to organic chemistry and analysis.
We've basically gathered everything from syllabus points to unit notes to give you a really solid walkthrough. Consider us your dedicated chemistry guides for this session.
Okay, let's jump straight in. Atomic structure 1.1. It's kind of amazing, isn't it, that atoms are mostly just empty space.
It really is counterintuitive.
Yeah.
But right at the center, there's this tiny, but very dense nucleus.
And that's where the protons and neutrons live.
Exactly. Protons and neutrons. And then the electrons are whizzing around that nucleus in, well, specific regions we call shells.
Right. So these particles, protons, neutrons, electrons, they have distinct properties.
Protons have a relative charge of +1, and a relative mass of about 1. Neutrons are neutral, 0 charge, but still have a relative mass of roughly 1.
And electrons.
Electrons are the odd ones out, mass-wise. They have a -1 charge, -1, but their mass is negligible in comparison. It's about 118/36 of a proton or neutron. Really tiny.
So like almost massless compared to the others.
Pretty much, yeah.
What defines an element then? What makes iron iron and not gold?
That comes down to the atomic number, which is also called the proton number. It's simply the number of protons in the nucleus. That number is unique to each element.
Okay, and the mass number?
The mass number, sometimes called the nucleon number, is the total count of protons plus neutrons in the nucleus. It tells you about the atom's mass.
So the mass is basically all concentrated in that tiny nucleus.
Almost entirely, yes. The nucleus holds the positive charge from the protons and nearly all the mass. The electrons, with their negative charge, occupy that much larger volume, the electron cloud, around the nucleus.
This is interesting. Imagine firing beams of these particles through an electric field. What would happen?
Good thought experiment. Well, because protons are positive, they'd curve towards the negative plate. Their path would bend.
Makes sense. Neutrons.
Neutrons have no charge, so they wouldn't be affected at all. They'd just go straight through.
And the electrons.
The electrons are negative and very light, so they'd be strongly attracted to the positive plate. You'd see a much more significant deflection compared to the protons because they have the same magnitude of charge, but much less mass.
That's a neat way to visualize their properties. Okay, so let's say we have, I don't know, an iron atom, Fe, or maybe an iron ion, like Fe. How do we work out how many protons, neutrons, and electrons it has?
It comes down to using those numbers we just defined. The atomic number tells you the number of protons that never changes for iron. For a neutral atom, the number of electrons equals the number of protons.
Okay.
For an ion, like Fe, the charge tells you about the electrons. That 2+ means it has lost 2 electrons compared to the neutral atom.
So it would have fewer electrons than protons.
Exactly, and the number of neutrons. You just subtract the atomic number, protons, from the mass number, protons plus neutrons. So for iron 56, atomic number 26.
It's 56 minus 26, 30 neutrons.
Precisely. So neutral Fe56 has 26 protons, 26 electrons, 30 neutrons. Fe would have 26 protons, 30 neutrons, but only 24 electrons.
Got it. Now, what about the size of atoms and ions? 1.1.7. Atomic radius isn't constant, is it?
No, definitely not. There are clear trends in the periodic table as you go across a period from left to right.
Like from sodium to chlorine.
Exactly. The atomic radius generally decreases.
Why is that?
Because you're adding more protons to the nucleus, increasing its positive charge. This stronger nuclear charge pulls the electrons in the same outer shell more tightly.
Even though you're adding electrons too?
Yes, because those electrons are going into the same main energy level, or shell. So the shielding effect from inner electrons doesn't increase enough to counteract the stronger pull from the nucleus. More pull, smaller atom.
Okay. What about going down a group, like lithium down to cesium?
Going down a group, the atomic radius increases.
Why the opposite trend?
2 main reasons. First, you're adding completely new electron shells further out from the nucleus. Second, these additional inner shells increase the shielding effect, blocking some of the nuclear charge from reaching the outermost electrons. Weaker pull, larger atom.
And ions, do they follow similar size rules?
Sort of. When a metal atom loses electrons to form a positive ion, a cautum.
Like na becoming no.
Yes, it gets smaller. Often, it loses its entire outer shell. Plus, with fewer electrons, there's less repulsion between them, so the remaining electron cloud shrinks.
And for negative ions, anions, like Cl becoming Sla.
They get larger. Adding extra electrons increases the repulsion between them, causing the electron cloud to expand.
Okay, that covers atomic structure basics. Let's shift to isotopes. 1.2. What are they exactly?
Isotopes are basically different versions of the same element. They have the same number of protons, that's what makes them the same element, but they have a different number of neutrons.
So, same atomic number, but different mass number.
Precisely.
And there's a specific way to write them down, right? The notation.
Yes, the standard notation is AZXX. X is the element symbol, Z is the atomic number down below, and A is the mass number up top.
So, carbon-12 would be 12-6Cl.
Perfect. And carbon-14, the radioactive one, is 14-6Cl. Same number of protons, 6 different number of neutrons, 6 versus 8.
Now, chemically speaking, do these different isotopes behave differently? Like, does carbon-14 react differently than carbon-12?
Generally, no. Chemical reactions depend almost entirely on the electron configuration, which is determined by the number of protons. Since isotopes of an element have the same number of protons, they have the same number of electrons arranged in the same way.
So, same chemical properties.
Essentially, yes. Their chemistry is identical for most practical purposes.
But they must differ in some way, otherwise why distinguish them?
They differ physically.
Hmm.
Because they have different numbers of neutrons, they have different masses.
Ah, okay.
So physical properties that depend on mass, like density or diffusion rate, will be slightly different between isotopes, but chemically they react the same way.
Right, let's dig into those electrons a bit more. 1.3 electrons, energy levels, and atomic orbitals. You mentioned shells earlier. Can we unpack that?
Sure. Think of electron shells as the main energy levels available to electrons around the nucleus. We call them principal energy levels, labeled with the number n equals 1, 2, 3, and so on. Higher n means higher energy and further from the nucleus.
And within these shells?
Within each main shell, except the first one, there are subshells, denoted by letters S, P, D, and F. These represent slightly different energy levels and different shaped regions within the main shell.
Okay, shells, then subshells. Anything else?
Yes, within each subshell there are orbitals. An orbital is a specific region of space where there's a high probability of finding an electron. Think of it like an electron's address.
And you mentioned the ground state.
The ground state is just the most stable, lowest energy arrangement of electrons for an atom or ion. It's how the electrons naturally fill up these shells, subshells, and orbitals.
How many orbitals are in each type of subshell? SPD.
An S subshell always contains just one orbital. A P subshell contains 3 orbitals, and a D subshell contains 5 orbitals.
And how many electrons can fit in each orbital?
Each single orbital, regardless of whether it's SP or D, can hold a maximum of 2 electrons.
So an S subshell holds 2 electrons max, P holds 6, 3 orbitals by 2 electrons, and D holds 10, 5 orbitals by 2 electrons.
Yeah.
What's the order they fill up in? Is it just 1s, then 2s, 2p3s, 3p3?
Almost, but there's a slight twist. The general order of increasing energy for the first few is 1s, then 2s, then 2p, then 3s, then 3p, but then comes 4s before 3.
Oh, okay. So 4s is lower energy than 3.
For filling purposes, yes. It's slightly lower in energy, so electrons occupy the 4's subshell before they start filling the third subshell. After 3 comes 4p, so the sequence is 1s, 2s, 2p3s, 3p4s, 3d4p.
And we use electron configurations to show this arrangement.
Yes. We write it out. For example, neon with 10 electrons is 1S-SO2 SO2PO. The number is the shell, the letter is the subshell, the superscript is the number of electrons in that subshell.
You also mentioned shorthand notation.
Right. We can use the electron configuration of the preceding noble gas as a shortcut. Iron, Fe 26 electrons, comes after argon, R 18 electrons. Argon's configuration is 1SO2 substitutes non SO2p3 is a 3p. So instead of writing all that out for iron, we write R and then add the remaining electrons, R4 carbon 2U.
Why do they fill 4s before 3? It seems counterintuitive.
It boils down to achieving the lowest overall energy for the atom. While the principal quantum number n is generally a good guide to energy, the energy levels of subshells in different shells can overlap. There's also the effect of inter-electron repulsion. It turns out that putting 2 electrons in the 4's orbital is slightly more stable, energetically favorable, than starting to put them into the 3rd orbitals for elements like potassium and calcium.
So it's about energy minimization and electrons repelling each other.
Precisely. It's a balance.
How does this work for ions, if we make FeO again?
When forming positive ions, especially for transition metals like iron, Electrons are removed from the highest principal energy level first. So even though 4s fills before third, when iron loses electrons to become Fe, the 2 electrons are lost from the 4s subshell.
Ah, okay. So Fio would be R30.
Exactly. The 4s electrons go first. For negative ions, you just add electrons to the next available orbital according to the filling order.
You mentioned electrons in boxes. What's that about?
It's a visual way to represent electron configurations. You draw boxes for each orbital, 1 box for S, 3 for P, 5 for D, and use arrows, usually half arrows, pointing up or down to represent the electrons and their spin.
Spin.
Yeah, electrons have a quantum mechanical property called spin, which can be thought of as spin up or spin down. The Pauli exclusion principle states that no 2 electrons in an atom can have the exact same set of quantum numbers. In practical terms for boxes, this means if 2 electrons are in the same orbital, same box, they must have opposite spins, 1 arrow up, 1 arrow down.
Okay. And there was another rule, Hund's rule.
Hund's rule applies when you have orbitals of the same energy, like the 3p orbitals or the 5d orbitals. It says that electrons will fill each orbital singly, with parallel spins, all pointing up, for example, before any orbital gets a second electron with the opposite spin. This minimizes repulsion.
Like getting your own seat on the bus before someone sits next to you.
Exactly like that. It's energetically more favorable.
What about the shapes of these orbitals, S and P?
S orbitals are simple. They're spherical. Electron density is the same in all directions from the nucleus. P orbitals are dumbbell-shaped. There are 3 of them, px, pi, y, pz, oriented along the x, y, and z axes, perpendicular to each other.
And briefly, what's a free radical?
A free radical is just any species, atom, molecule, or ion that has 1 or more unpaired electrons. That unpaired electron makes them very reactive.
Okay, that clarifies electrons. Let's talk about removing them. Ionization energy, 1.4. What's the first ionization energy?
The first ionization energy, i.e. Ri, is very specifically defined. It's the minimum energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of singly charged gaseous positive ions.
Gaseous state is important then.
Crucial. And it always requires energy input, so it's an endothermic process. AH is positive.
And we can keep removing electrons. Second, third ionization energies.
The second ionization energy, i.e., is the energy to remove an electron from 1 mole of gaseous plus 1 ions to make plus 2 ions, X or G plus E, and so on for subsequent ionizations.
Does it get harder or easier to remove more electrons?
Much harder. Each successive ionization energy is significantly larger than the previous one. You're pulling a negative electron away from an increasingly positive ion.
Okay, trends again. How does IE change across a period?
Generally, the first ionization energy increases as you go across a period.
Because the nucleus is pulling harder and the atom is smaller.
Exactly. Increased nuclear charge and decreased atomic radius mean the outer electron is held more tightly. It takes more energy to remove it. There are little dips, though.
Dips? Why?
Sometimes, removing an electron breaks up a particularly stable configuration, like a full or half-full subshell. For example, it's slightly easier to remove an electron from oxygen than nitrogen, even though oxygen is further across. This is because oxygen has a paired electron in one of its 2p orbitals, and removing that paired electron relieves some electron repulsion. Nitrogen has a half-filled 2p subshell, 1 electron in each orbital, which is relatively stable.
Interesting. And down a group?
Down a group, i.e. or generally decreases. The outer electron is further from the nucleus, larger atomic radius, and is better shielded by inner electrons. It's held less tightly, easier to remove.
You said successive ionization energies always increase, but sometimes there are huge jumps. Why?
Ah, yes. Those big jumps are very informative. They occur when you start removing an electron from a new inner shell, one that's much closer to the nucleus and experiences significantly less shielding.
So, like going from removing valence electrons to core electrons.
Precisely. Those core electrons are held much, much more tightly. Seeing a huge jump tells you you've just broken into a stable inner shell.
So fundamentally, ionization energy is about the pull between the nucleus and the outer electrons.
It's all about overcoming that electrostatic attraction between the positive nucleus and the negative electron you're trying to remove.
What factors summarize this attraction strength?
Key factors are 1. Nuclear charge, more protons, stronger pull equals higher, i.e. 2. Atomic radius, electron further away, weaker pull equals lower, i.e. Free, shielding, more inner shells, weaker effective pull on outer electrons equals lower, i.e. 4. Electron-electron repulsion, sometimes called spin pair repulsion, which can make it slightly easier to remove a paired electron, causing small dips in trends.
So looking at a list of successive ionization energies for an element could tell us a lot.
Absolutely. The pattern, especially those large jumps, allows you to deduce the electron configuration.
Oh.
You count how many electrons were removed relatively easily before the first huge jump. That number tells you how many valence electrons the atom has.
And that helps place it in the periodic table.
Yes. The number of valence electrons corresponds to the group number for main group elements, and the energy scale of the ionization energies gives you an idea of which period it's in. It's like a fingerprint.
Okay, let's move from individual atoms to measuring their masses relative. 2.1 relative masses. What's the baseline we use?
We use the Unified Atomic Mass Unit, symbol U, or sometimes AMU. It's defined as exactly 1/12 the mass of a single neutral atom of carbon-12.
So everything is compared back to carbon-12.
Exactly. It gives us a standard scale.
And we have several relative mass terms, R, Mr.
Yes. Relative atomic mass, R, is the weighted average mass of an element's naturally occurring isotopes relative to 112th the mass of a carbon-12 atom. The weighted average part is key. It accounts for how abundant each isotope is.
Okay, what about relative isotopic mass?
That's simpler. It's just the mass of one specific isotope relative to 112th of carbon-12.
Then relative molecular mass, Mr.
That's for molecules. You just add up the relative atomic masses of all the atoms in the molecule's formula.
And for ionic compounds, they don't form molecules.
Right. For ionic compounds like NaCl, we use relative formula mass. It's the same idea.
Yeah.
Sum the R values of all the ions in the empirical formula unit.
Okay. Now, how do we count large numbers of these atoms or molecules? That's the mole rate. 2.2, the mole and Avogadro constant.
Precisely. Dealing with individual atoms is impossible in the lab, so we use the mole. 1 mole is defined as the amount of substance containing the same number of elementary entities, atoms, molecules, ions, whatever, as there are atoms in exactly 12 grams of carbon-12.
And that magic number is Avogadro's constant.
Yes, Avogadro's constant, Na or L, is the number of entities in 1 mole. Its value is approximately 6.02 by $10,000 per mole. It's a huge number, but it provides the bridge between the atomic scale and the macroscopic scale we work with.
So a mole of anything contains 6.02 by 10 suts of those things.
Yes, a mole of carbon atoms, a mole of water molecules, a mole of sodium ions, they all contain that same number of particles.
Moving on to formulas, 2.3, empirical versus molecular formula, what's the difference?
The empirical formula gives the simplest whole number ratio of atoms of each element in a compound. For example, glucose has a molecular formula, C euros. Its empirical formula is CHO, representing the 1.2.1 ratio.
And the molecular formula?
The molecular formula shows the actual number of atoms of each element in one molecule of the compound. So CEHO is the molecular formula for glucose. It's always a whole number multiple of the empirical formula.
We also see terms like anhydrous and hydrated. What do they mean?
Anhydrous means without water. A hydrated compound is an ionic solid that has water molecules incorporated into its crystal lattice structure in a fixed ratio.
Like copper sulfate crystals being blue.
Exactly. That blue color is often due to hydrated copper sulfate, CuSO.5Hu. The 5Hu represents the water of crystallization. 5 water molecules are chemically bound within the crystal for every CuSO unit. If you heat it, the water is driven off, and you get anhydrous copper sulfate, CuSO, which is white.
Can we work out these formulas from experimental data?
Yes. If you have the percentage composition by mass, or the mass of each element in a sample, you can convert those masses to moles, find the simplest mole ratio, and that gives you the empirical formula.
And the molecular formula?
To get the molecular formula, you also need the compound's molar mass, or relative molecular mass. You calculate the mass of the empirical formula unit and see how many times it fits into the actual molar mass. That multiple gives you the molecular formula.
Okay, let's apply this to reactions. Reacting masses and volumes, 2.4. This is stoichiometry.
Yes, stoichiometry is the calculation of quantities in chemical reactions using balanced chemical equations. The coefficients in a balanced equation tell you the mole ratios in which substances react and are formed.
So we can predict how much product we'll get from a certain amount of reactant.
Absolutely. Using molar masses to convert between grams and moles, and using the mole ratios from the balanced equation, you can calculate reacting masses. You can figure out, say, how many grams of product C you can make from X grams of reactant A.
What about percentage yield?
Percentage yield compares how much product you actually got in an experiment, the actual yield, to the maximum amount you theoretically could have gotten based on stoichiometry. the theoretical yield.
Yeah.
It's actual yield, theoretical yield, by 100%. It's rarely 100% in practice due to side reactions, incomplete reactions, or losses during purification.
How do we handle volumes, especially for gases and solutions?
For gases, we can use the ideal gas law, PV-nRT, to relate moles to volume, pressure, and temperature. Or under standard conditions, we can use the molar volume of a gas. Example, about 24 dm mole at room temperature and pressure. For solutions, we use concentration, usually molarity, moles per dmR or moles per liter. Molarity equals moles volume. This allows us to calculate the moles of a substance in a given volume of solution.
In reactions, sometimes one reactant runs out before the others.
Right, that's the limiting reagent, or limiting reactant. It's the reactant that gets completely consumed first and therefore limits the maximum amount of product that can be formed. Any other reactants left over are called excess reagents.
How do you identify the limiting reagent?
You need to compare the mole ratios of the reactants you actually have with the mole ratios required by the balanced equation. Calculate the moles of each reactant you start with. Then, use the stoichiometry to see which one would run out first based on how much of the other reactant it needs to react with completely. All calculations of theoretical yield should be based on the initial amount of the limiting reagent.
And can we use these calculations to deduce the reaction equation itself?
Yes, if you carefully measure the amounts, masses, volumes, concentrations of reactants consumed and products formed in a reaction, you can work backwards to determine the mole ratios. This allows you to deduce the stoichiometric coefficients and write the balanced chemical equation for the reaction.
Okay, great. Let's move into bonding, Chapter 3. Starting with electronegativity, 3.1. What's the core idea here?
Electronegativity is basically a measure of how strongly an atom attracts the bonding pair of electrons towards itself when it's part of a covalent bond.
What makes one atom better at pulling electrons than another?
Three main factors. Nuclear charge more protons means a stronger pull. Atomic radius, smaller atoms can get closer to the bonding electrons, increasing the pull. And shielding inner electrons block some of the nuclear charge, reducing the pull on the outer bonding electrons. Less shielding means higher electronegativity.
And how does electronegativity vary across the periodic table?
It generally increases across a period, left to right, because nuclear charge increases significantly while the radius decreases. It generally decreases down a group because even though nuclear charge increases, the increasing atomic radius and shielding effects are more dominant. Fluorine is the most electronegative element.
How does this help predict bond types? Ionic versus covalent.
The difference in electronegativity between two bonding atoms is key. A very large difference means one atom pulls the electrons so strongly that it essentially takes them, forming ions in ionic bond, like NaNCl. A very small difference means the electrons are shared relatively equally, a nonpolar covalent bond, like in Ki or H. An intermediate difference means unequal sharing a polar covalent bond, like in HCl or HO, where one end of the bond is slightly positive and the other slightly negative.
Let's focus on ionic bonding, 3.2. It's about charged ions attracting.
Exactly. It's the electrostatic force of attraction between oppositely charged ions, positive castrications, and negative anions formed by the transfer of electrons, usually from a metal to a nonmetal.
Can you give classic example?
Sodium chloride, NaCl, is the classic. Sodium loses an electron, NiO. Chlorine gains one, CO, and the strong attraction holds them in a crystal lattice. Magnesium oxide, MgO, is another. Mg loses 2 electrons. Mg whilst on oxygen gains 2. The 2 plus and 2 charges lead to even stronger attraction than in NaCl. Calcium chloride, KaL, involves Cal losing 2 and 2 chlorine atoms, each gaining 1, 2xAO.
Okay, now for covalent bonds, let's consider their strength and length, 3.4. What's bond energy?
Bond energy, or bond enthalpy, is the energy needed to break 1 mole of a specific type of covalent bond in the gaseous state. It's a measure of bond strength. Higher bond energy means a stronger bond.
And bond length?
Bond length is simply the average distance between the nuclei of 2 covalently bonded atoms. Generally, shorter bonds are stronger bonds, so there's often an inverse relationship between bond length and bond energy.
How does this relate to reactivity?
Molecules with weaker bonds, lower bond energies, tend to be more reactive because it takes less energy to break those bonds, which is often the first step in a reaction. If a molecule has particularly weak bonds, that's likely where it will react first.
Molecules aren't flat diagrams. Let's talk shapes, 3.5, and VS pair theory.
Right. VS here stands for valence shell electron pair repulsion. The basic idea is that pairs of electrons in the valence shell of a central atom, both bonding pairs involved in covalent bonds and non-bonding lone pairs, repel each other and will arrange themselves in 3D space to be as far apart as possible, minimizing repulsion.
And this arrangement dictates the molecule's shape.
Yes, the arrangement of all electron pairs, bonding and lone pairs, determines the electron pair geometry. The actual molecular shape is determined by the positions of the atoms only.
Can we run through some examples? BF.
Boron trifluoride. Boron has 3 valence electrons, forms 3 single bonds with fluorine. So 3 bonding pairs, Vero lone pairs around boron. To get furthest apart, they adopt a trigonal-planar shape. Bond angles are 120 degrees. Carbon dioxide. Carbon forms 2 double bonds with oxygen. We treat each double bond as 1 region of electron density. So 2 regions around carbon. They get furthest apart by being linear, 180-degree bond angle.
Methane, CH.
Carbon forms 4 single bonds to hydrogen. 4 bonding pairs, 0 lone pairs. They arrange tetrahedrally. Bond angles are 109.5 degrees.
Ammonia.
Nitrogen has 5 valence electrons. Forms 3 bonds to hydrogen, 3 bonding pairs, leaving 1 lone pair. Total 4 electron pairs, so the electron pair geometry is based on a tetrahedron. But the shape is described by the atoms only, which form a trigonal pyramid. The lone pair repels more strongly than bonding pairs, so the HNH bond angles are slightly less than 109.5 degrees, about 107 degrees.
Water who?
Oxygen has 6 valence electrons, forms 2 bonds to hydrogen, 2 bonding pairs, leaving 2 lone pairs. Again, 4 electron pairs total, so electron pair geometry is tetrahedral based. But with 2 lone pairs, the shape is bent or V-shaped. The 2 lone pairs compress the HOH angle even more, down to about 104.5 degrees.
More complex ones.
Yeah.
SFU.
Sulfur hexafluoride. Sulfur forms 6 bonds to fluorine, 6 bonding pairs, 0 lone pairs. They arrange octahedrally with 90-degree angles.
PF.
Phosphorus pentachloride. Phosphorus forms 5 bonds to chlorine, 5 bonding pairs, 0 lone pairs. This gives a trigonal bipyramidal shape. It has 2 different bond angles, 120 degrees between the 3 equatorial chlorines in the plane, and 90 degrees between the axial chlorines, top and bottom, and the equatorial ones.
So we can predict shapes for similar molecules too.
Yes, using the number of bonding and lone pairs around the central atom, you can apply VSPJ pair to predict the shapes and approximate bond angles for many analogous molecules and ions.
These shapes and bond polarities lead to forces between molecules, right? Intermolecular forces, 3.6.
Exactly. Intermolecular forces, IMFs, are attractions between separate molecules. They're much weaker than the covalent or ionic bonds within molecules, but they're crucial for determining physical properties like melting and boiling points.
What's the general term we use?
Van der Waals forces is often used as an umbrella term for all intermolecular forces.
What are the specific types?
Okay, there are 3 main types to know. First, London dispersion forces, also called instantaneous dipole-induced dipole forces. These exist between all molecules, even nonpolar ones. They arise from temporary random fluctuations in electron distribution that create fleeting dipoles, which then induce dipoles in neighbors. They're generally weak, but increase with the size and number of electrons in the molecule.
Second type.
Permanent dipole forces. These occur only between polar molecules, molecules that have an overall permanent separation of charge due to polar bonds and an asymmetrical shape. The positive end of one molecule attracts the negative end of another, stronger than London forces for similar-sized molecules.
And the third, very important one.
Hydrogen bonding. This is a special, extra-strong type of permanent dipole-dipole interaction. It happens specifically when hydrogen is bonded to a very electronegative atom, nitrogen, oxygen, or fluorine, NO or F.
Like in water or ammonia.
Exactly. The H bonded to N, O, or F becomes very partially positive, plus atom, and is strongly attracted to a lone pair of electrons on an N, O, or F atom of a neighboring molecule.
And this hydrogen bonding explains water's weird properties.
It does. Water's relatively high melting point, boiling point, and surface tension are all due to the strong hydrogen bonds needing more energy to overcome. Even the fact that ice floats that ice is less dense than liquid water is because hydrogen bonds force the molecules into an open lattice structure in the solid state.
So electronegativity, polar bonds, molecular shape, polarity, intermolecular forces, physical property, it's all linked.
It's a beautiful chain of cause and effect.
And just to confirm, these intermolecular forces are weaker than actual chemical bonds.
Oh, much weaker. Covalentionic bonds are hundreds or thousands of kjohns. IMFs are typically just tens of kjohm. That's why boiling water breaks IMFs, but doesn't break the HO covalent bonds within the water molecules.
Finally, for bonding, dot and cross diagrams, 3.7, why use them?
They're a simple visual tool to show how valence electrons, outer shell electrons, are involved in bonding. Dots for electrons from one atom, crosses for electrons from the other.
How do they show ionic bonding?
For ionic bonding, they show the transfer of electrons, one atom losing its dots crosses, the other gaining them, resulting in ions with full outer shells and opposite charges. The attraction is then implied.
And covalent.
For covalent bonding, they show the sharing of electrons between atoms, with pairs of dots crosses representing the shared pairs in the covalent bonds. They can also show coordinate-dated bonds, where one atom provides both electrons in the shared pair. You can draw them for all the molecules we discussed in VSE way, even those with expanded octets like SF here.
Okay, let's move to states of matter, starting with gases. 4.1. What causes gas pressure?
It's simply the result of gas molecules constantly colliding with the walls of their container. Each collision exerts a tiny force, and the sum of all these forces over an area is the pressure we measure.
We often talk about ideal gases. How are they different from real gases?
An ideal gas is a theoretical model. It assumes two main things. One, the gas particles themselves have zero volume, and two, there are absolutely no attractive or repulsive forces between the particles.
Which isn't really true, is it?
No, real gas particles do have volume, and they do experience intermolecular forces. However, the ideal gas model works very well for real gases at low pressures and high temperatures.
Why those conditions?
At low pressure, the particles are far apart, so their individual volume is negligible compared to the container volume. At high temperature, the particles have high kinetic energy, easily overcoming any weak intermolecular attractions.
And the equation that describes ideal gases.
That's the ideal gas equation. PV equals the number of moles, N, times the ideal gas constant, times the absolute temperature, T in Kelvin.
And we can use this for a calculation.
Absolutely. If you know three variables, you can find the fourth. You can also rearrange it to find the molar mass of a gas if you measure its mass. M, volume, pressure, and temperature. Mr. MRT, PV.
Let's look at solids now, 4.2. How are particles arranged in different types of solid lattices, starting with giant ionic solids?
Giant ionic solids like NaCl or MgO consist of a regular repeating 3D lattice of positive and negative ions held together by strong electrostatic forces acting in all directions. High melting points, often brittle.
What about simple molecular solids, like iodine or ice?
These are made of discrete molecules, like I0 or H0, held in fixed positions in the lattice by weak intermolecular forces. London forces for iodine, hydrogen bonds for ice. Because the forces between molecules are weak, they tend to have low melting points.
And giant molecular or covalent solids, diamond, graphite, silicon dioxide.
These have atoms joined together by strong covalent bonds extending throughout the entire crystal, forming a huge network. No discrete molecules. To melt them, you have to break strong covalent bonds, so they have very high melting points and are often very hard, like diamond or Si-Oro. Graphite is an exception with its layered structure.
Tell me more about graphite's structure.
Graphite has layers of carbon atoms arranged in hexagonal rings, strongly covalently bonded within each layer. However, the forces between the layers are weak van der Waals forces. This allows the layers to slide, making graphite a lubricant. It also has delocalized electrons within the layers, allowing it to conduct electricity.
Lastly, giant metallic solids, like copper.
Metals consist of a regular lattice of positive metal ions surrounded by a sea of delocalized valence electrons. These electrons aren't fixed to any one ion and can move freely throughout the lattice. The attraction between the positive ions in this electron sea is the metallic bond. It's strong, and the mobile electrons explain why metals conduct heat and electricity well, and why they're malleable and ductile.
Right, halfway point. Let's discuss energy changes in reactions. Enthalpy, 5.1. What is enthalpy change, Emmy?
Enthalpy change is the heat energy change measured at constant pressure during a chemical reaction. If heat is released, it's exothermic and ADH is negative. If heat is absorbed, it's endothermic and ADH is positive.
We often see reaction pathway diagrams. What do they show?
They plot energy against the progress of a reaction. They show the relative energy of reactants and products. The difference is no DH. They also show the activation energy, EA, which is the energy barrier, the peak that reactants must overcome to turn into products.
What are standard conditions in thermochemistry?
Standard conditions are a reference point. They are defined as 298 Kelvin, 25 degrees C, and 101 kilopascals, 1 atm pressure. Enthalpy changes measured under these conditions get a special symbol, often a superscript plimsoll or theta.
And there are specific types of standard enthalpy changes. Formation, combustion.
Yes. Standard enthalpy change of reaction, the MO in D20 by 820 by 99, is the overall change for a specific reaction. Standard enthalpy change of formation, HA divided by E20 by 820 by 820 by 99 is when 1 mole of a compound is formed from its elements in their standard states. Standard enthalpy change of combustion, note E80 by 820 by 820 by 99, is when 1 mole of a substance burns completely in oxygen. Standard enthalpy change of neutralization, note E80 by E20 by 820 by 99, is when 1 mole of water is formed from an acid and a base.
Why do reactions involve energy changes at all?
It's all about bond breaking and bond making. Breaking bonds always requires energy input, endothermic. Making bonds always releases energy, exothermic. The overall APH is the net balance between the energy needed to break reactant bonds and the energy released when product bonds form.
Can we estimate APH using bond energies?
Yes, approximately. You can calculate the total energy needed to break all the bonds in the reactants and subtract the total energy released when all the bonds in the products are formed. A bond energy is broken, a key bond energy is formed. Remember, bond energies are always positive values for breaking bonds.
Why only approximately?
Because tabulated bond energies are often average values for a particular type of bond, like CH, across many different molecules. The actual energy of a specific bond can vary slightly depending on its molecular environment. It's exact only for diatomic molecules.
Can we measure enthalpy changes experimentally?
Yes, using calorimetry. You carry out the reaction in an insulated container, calorimeter, and measure the temperature change of the surroundings, usually water or a solution. Using the equation Q, A equals dt, where Q is heat, M is mass, C is specific heat capacity, you find the heat exchanged. Then AHFOQN, where N is the moles of the limiting reactant, gives the enthalpy change per mole. Hess's law, 5.2, seems useful for finding AH values indirectly. What's the principle? Hess's law states that the total enthalpy change for a reaction is the same, no matter which route is taken from reactants to products. Enthalpy is a state function, only the start and end points matter, not the path. How do we use it? We can construct energy cycles, showing different pathways between reactants and products. Or we can manipulate known thermochemical equations. Reversing them reverses the sign of EDH, multiplying them multiplies H, and add them together algebraically to arrive at the target reaction equation. The sum of the manipulated AH values gives the H for the target reaction. It's great for finding AH for reactions hard to measure directly. You can also incorporate bond energy data into Hess cycles.
Okay, switching topics to redox, 6.1. What are oxidation numbers?
Oxidation numbers, or oxidation states, are a way of keeping track of electron gain or loss in reactions, even in covalent compounds. They represent the hypothetical charge an atom would have if all its bonds were purely ionic.
How do we assign them?
There's a set of rules. For example, elements are zero. Simple ions have an oxidation number equal to their charge. Oxygen is usually -2, except in peroxides. Hydrogen is usually +1, except in metal hydrides. The sum of oxidation numbers in a neutral compound is 0. In an ion, it equals the ion's charge.
And how do they relate to redox?
Oxidation is defined as an increase in oxidation number, loss of electrons. Reduction is defined as a decrease in oxidation number, gain of electrons. In any redox reaction, both must occur.
Let's talk about equilibrium, 7.1. What makes a reaction reversible?
A reversible reaction is one that can proceed in both the forward, reactants to products, and reverse products to reactants directions simultaneously. We show this with a double arrow.
What is dynamic equilibrium?
It's the state reached in a reversible reaction when the rate of the forward reaction becomes exactly equal to the rate of the reverse reaction. At this point, the concentrations of reactants and products remain constant, even though reactions are still occurring in both directions. It's dynamic, not static.
Does it require specific conditions?
Yes. Crucially, it must occur in a closed system, meaning no matter escape can enter or leave. Otherwise, products escaping would prevent the reverse reaction from keeping pace.
The Chatouillet's principle helps predict shifts in equilibrium. What's the core idea?
It states that if you impose a change on a system at equilibrium, the system will shift its equilibrium position in a way that tends to counteract or relieve that stress.
How does temperature affect it?
If you increase the temperature, the equilibrium shifts in the direction that absorbs heat, endothermic direction, to cool things down. If you decrease the temperature, it shifts in the heat-releasing exothermic direction.
What about concentration changes?
If you add more reactant, the equilibrium shifts forward to use it up. If you add more product, it shifts backward to use that up. Removing a reactant shifts it backward. Removing a product shifts it forward. The system tries to restore the balance.
And pressure changes. For gases?
Increasing pressure shifts the equilibrium toward the side with fewer moles of gas, as this reduces the overall pressure. Decreasing pressure shifts it towards the side with more moles of gas. If the number of gas moles is equal on both sides, pressure has no effect on the position of equilibrium.
Does a catalyst affect the position of equilibrium?
No. A catalyst speeds up both the forward and reverse reactions equally. It helps the system reach equilibrium faster, but it doesn't change where the equilibrium lies, i.e. the final concentrations.
We can quantify equilibrium with Kc 7.1.4. How's that expressed?
Oh. Kc is the equilibrium constant in terms of concentrations. For a general reaction, AA plus BB or CC plus DD, Kc equals CCDD, AABB, where the square brackets denote equilibrium concentrations in mole DO. Importantly, you only include species in the gas or aqueous phase. Solids and pure liquids are left out as their concentration is effectively constant.
And for gases, we can use Kp 7.1.6 based on pressure.
Yes, Kp uses partial pressures instead of concentrations. Partial pressure is the pressure a gas would exert if it were alone in the container, mole fraction x total pressure. For the same reaction with gases, KPCPD, PAPBD, where Px is the partial pressure of gas x at equilibrium.
Can we calculate equilibrium concentrations using Kc or Kp?
Yes. If you know the initial amounts and the value of Kc or Kp, you can set up an ICE table, initial change equilibrium, to figure out the equilibrium concentrations or partial pressures. Or, if you measure the equilibrium amounts, you can calculate the value of Kc or Kp.
Do Kc and Kp values change if we change conditions?
Only temperature changes the value of Kc or Kp. Changes in concentration or pressure will shift the position of equilibrium, altering individual concentrations pressures.
Right.
But the ratio defined by Kc or Kp remains constant at a fixed temperature. Catalysts have no effect on the value of Kc or Kp.
Can you give examples of industrial processes using these principles?
The Haber process for making ammonia, N plus 3 H zeros, 2 NHRs, is a classic. It's exothermic. High pressure is used to favor the product side, fewer moles of gas. A moderate temperature is a compromise. Lower temps give better yield but are too slow, so a catalyst iron is used to speed it up. The contact process for sulfuric acid, 2SeUROs plus OUS2SAC, is similar. Moderate pressure, catalyst via at moderate temperature. Optimizing yield and rate is key.
Let's move to acids and bases, 7.2. What's the Brønsted-Lowry definition?
Simple and useful. An acid is a proton H donor. A base is a proton H acceptor. Reactions involve proton transfer.
Remind us of common acids and alkalis.
Acids: HCl hydrochloric, HSO sulfuric, HNO nitric, ethanoic acetic. Alkalis, soluble bases: NaOH, sodium hydroxide, KOH, potassium hydroxide, and H ammonia.
What's the difference between strong and weak acid bases?
Strong acid bases fully dissociate ionize in water, HCl plus Cl, NaOH, NaO plus OH. Weak acid bases only partially dissociate, establishing an equilibrium NHO will true co, NHO plus OH. This affects pH, definitely. Strong acids give a much lower pH than weak acids of the same concentration because they produce far more HO ions. Strong bases give a much higher pH than weak bases. Remember, pH 7 is acidic, pH 7 is alkaline, pH 7 is neutral, pure water.
Are there other differences? Reaction rates, conductivity?
Yes. Strong acids react faster with metals, more HO available. Strong acids bases are better electrical conductors, more ions in solution. You can see these differences with indicators, pH meters, or conductivity measurements.
What happens in neutralization?
Fundamentally, H ions from the acid react with OE ions from the base to form water. HAK plus OH, HAHOL.
And what else is formed?
A salt. The salt is formed from the cation of the base and the anion of the acid, e.g. NiO from NaOH and ClAl from HDl form HAIL.
Okay, shifting to reaction speed. Rates of reaction, 8.1. How is rate defined?
Rate of reaction is the change in concentration of a reactant or product per unit time. Usually units of mole DMIO, how fast stuff gets used up or made.
What affects the rate, concentration, and pressure?
Yes, higher concentration or pressure for gases means more particles in a given volume, leading to more frequent collisions between reactive particles, hence a faster rate. Collision theory is key here.
How do we measure rate?
By monitoring concentration changes over time, plot concentration versus time. The rate at any point is the gradient slope of the tangent to the curve at that point. Rate usually decreases as reactants get used up.
Temperature has a big effect on rate, 8.2. Why? Activation energy.
Yes. Activation energy, EA, is the minimum energy colliding particles need to react. Temperature affects rate in two main ways.
Okay, what are they?
First, higher temperature means particles move faster, so they collide more frequently. Second, and more importantly, it drastically increases the proportion of particles that have energy greater than or equal to the activation energy. We see this using the Boltzmann distribution curve.
Explain the Boltzmann distribution.
It shows the distribution of kinetic energies among molecules at a given temperature. It's a curve starting at 0, rising to a peak, then tailing off. Only the molecules in the tail end, beyond the activation energy mark, have enough energy to react upon collision.
So increasing temperature shifts that curve.
It shifts the curve to the right and flattens it, meaning a much larger fraction of molecules now have energy OPIA. So many more collisions are effective, leading to a much faster rate. A small temperature increase can cause a large rate increase.
What about catalysts, 8.3? How do they speed things up?
Catalysts provide an alternative reaction pathway with a lower activation energy. They aren't used up in the reaction.
Lower EA means?
Lower E means, according to the Boltzmann distribution, a much larger fraction of molecules have enough energy to react via the catalyzed pathway at the same temperature. More effective collisions, faster rate.
Can we see this on a reaction pathways
So-
diagram?
Yes, the catalyzed pathway shows a smaller hump, a lower EA, compared to the uncatalyzed one. But the start reactants and end products, energy levels are the same, so EH is unchanged.
What are homogeneous and heterogeneous catalysts?
Homogeneous catalysts are in the same phase as the reactants, example, liquid catalyst in a liquid reaction. Heterogeneous catalysts are in a different phase, e.g. solid catalyst for a gas reaction like iron in the Haber process. Heterogeneous catalysis often involves reactants absorbing onto the catalyst surface.
Right, into inorganic trends now. Period 3, physical properties, 9.1, sodium to argon, atomic radius.
Decreases across the period. Increasing nuclear charge pulls electrons tighter.
Ionic radius.
Also generally decreases for the positive ions, Nali to OO, and for the negative ions, Pu to Ku. But there's a big jump up in size when you go from cation allo to anion.
Melting point.
Increases from NO, MG, AL, stronger metallic bonds. Peaks at C, giant covalent, then drops dramatically for P. 0xe20 by A20 by 88. ANMU, KLO, simple molecular, weak IMFs, and R, very weak IMFs.
Electrical conductivity.
High for metals, Na and MEL, delocalized electrons, C is
Wow.
semiconductor, PS, CLR are essentially non-conductors.
How do structure and bonding explain melting point and conductivity?
Metals, giant lattice, strong metallic bonds, delocalized electrons, high MP, high conductivity,
Yeah.
silicon, giant covalent network, very high MP, semiconductor. PSCLR, simple molecules, weak IMFs, low MP, non-conductors.
Now, period 3, chemical properties, 9.2. Reactions with oxygen, chlorine, water.
Oxygen, form oxides like natto, MgO, alloros, CO euros, azo euros, serine, form chlorides, NaCl, MgCl, allos, cyclo, PClO, water. Now reacts vigorously, NaOH plus H. Mg reacts with steam, MgO plus H. Others generally don't react readily with water itself, but their oxide chlorides do.
Oxidation number trends in oxychlorides.
Generally increases across the period, corresponding to the number of valence electrons. Now plus 1, Mg plus 2, L plus 3, SAM plus 4, P plus 5, S plus 4 plus 6.
How do the oxides react with water? Acid-base nature?
NaFO, basic forms NaOH, pH 13-14, MgO, basic forms MTOH, pH 9-10, Aluros, amphoteric, doesn't react readily with water, CO Eros, acidic, forms weak acid, PO Euro, acidic, forms ASPO, pH 1, So acidic, form HO So Euro, pH 1 to 3, Trend, basic, amphoteric, mesocytic.
And the oxide hydroxides themselves.
NaOH, strong base.
Yeah.
MgOH, weak base. Alphateric react with both acids and strong bases. SaO acidic, PS oxides acidic.
How do the chlorides react with water? pH of solution.
NaCl dissolves, neutral pH 7. MgCl dissolves, slightly acidic pH 5-6 due to MVHO hydrolysis. Alkyl dissolves, acidic pH 2-3 due to alkyl hydrolysis. Sickle reacts violently, forms NCIOs plus HLIQ, very acidic pH 1. PCl reacts violently, forms HPLs plus HClAQ, very acidic pH 1. Trend, neutral weakly acidic LAHPL, but very acidic hydrolysis. What explains these chemical trends across period 3? It's the change in bonding from ionic metallic on the left to covalent on the right. Also, increasing electronegativity and charge density influence the interactions with water, hydrolysis, and the acid-base nature of the oxides.
Can we predict bonding type from properties?
Yes. High MP basic oxides suggest ionic NaOH, NaCl. Low MP BP acetic oxide hydrolyzing chlorides suggest covalent, Zekel PO show. Intermediate amphoteric behavior suggests intermediate bonding character, alkaline.
Yeah. Okay, let's focus on group 2. Alkaline earth metals, 10.1. How do they react generally?
They're reactive metals. React with oxygen, form MO. Reactivity with water increases down a group. Mg slow with cold, Kaiser BAV for faster, forming MOH plus HR. React with acids, form salt plus HR. Reactivity increases down group. Exception, queso insolubility can slow reaction with H0.
How do their oxides, hydroxides, carbonates react?
Oxides, MO, are basic, except BeO, react with acid. Hydroxides, MOH, are basic, react with acid. Solubility increases down group. Carbonates, MCO, react with acid. Salt plus A purose plus E agerose.
What about heating their nitrates and carbonates?
Thermal decomposition. Nitrates, MaO plus 2 MEOO plus AEO. Carbonates, MEO plus CoO. Thermal stability increases down the group for both, due to decreasing polarizing power of the larger MOO ions down the group.
Are there clear trends down group too?
Yes. Reactivity increases down group, lower, i.e. basicity of oxide hydroxides increases. Thermal stability of carbonates, nitrates increases. Melting point generally decreases. Weaken metallic bonding.
What about solubility trends for hydroxides and sulfates?
Opposite trends. Hydroxide solubility increases down the group. MgOH least soluble, BOH is most. Sulfate solubility decreases down the group. MgSO most soluble, least soluble, insoluble. Remember, sulfate solubility slumps.
Now for group 17, halogens, 11.1, 11.4, physical properties, color, volatility.
Colors: Oro, pale green gas, Bayo, red-brown liquid, Iler, dark solid purple vapor. Volatility decreases down group. Color, bare Ro, adduces due to increasing strength of London dispersion forces between the larger molecules with more electrons. Bond strength, X, decreases down group, ELO, bare I, due to increasing size.
Chemical properties, oxidizing agents.
Strong oxidizing agents want to gain one electron. Reactivity as oxidizing agents decreases down group, F, Kelio, bare Ri, due to decreasing electronegativity, increasing size.
Reaction with hydrogen, stability of HX.
Form hydrogen halides. Reactivity with HF decreases down group. Thermal stability of the HX also decreases down group, HF, HCl, HHBr, because the HX bond gets weaker longer.
What about halide ions, Cl, RMIO, acting as reducing agents?
They can lose electrons. Reactivity as reducing agents increases down group, F, Cli, Bra. Larger ions lose electrons more easily.
How do we see this reducing ability in reactions?
Reaction with concentrated HSO is key. Clay just forms HCl gas. Bra forms HBr, but HBr reduces HSO to SO, Bra oxidized to I. I forms HI, which is a strong enough reducing agent to reduce HASL further to HARs SS, SOI oxidized to I.
How do we test for halide ions in solution?
Add aqueous silver nitrate. AgCl dissolves in dilute NHAir. AgCl dissolves in dilute NHAir. AgR equals yellow PPT, insoluble in NH.
What about chlorine's disproportionation reactions?
Chlorine reacts with cold dilute NaOH to form NaCl. Cl is NaClO1 reduced, and NaClO, sodium hypochlorite. Cl is +1 oxidized. Cl is +2 NaOH. It forms NaCl plus NaClA plus NaClB. Cl is +5, more oxidized. 3 FlaLO plus 6 NaOH. 5 NaCl plus NaClA plus 3 HO.
And chlorine in water purification.
Chlorine reacts with water. Class Keats zeros plus HCl plus HOCl, hypochlorous acid. HOCl is the active disinfectant, or its ion ClO, killing bacteria by oxidation.
Nearly there. Nitrogen and sulfur, 12.1. Why is N so unreactive?
Because of the very strong Na triple bond, high bond energy, and the molecule being nonpolar. Takes a lot of energy to break that bond.
How is ammonia basic?
Brønsted-Lowry base. It accepts a proton using the lone pair on the nitrogen atom, forming the ammonium ion, NHO plus ORO.
What's the structure of the ammonium ion, NHO?
Tetrahedral, nitrogen bonded to 4 hydrogens. One bond is a coordinate bond formed using the lone pair, but all 4 NH bonds become equivalent once formed.
How can we get ammonia back from ammonium salts?
React the salt with a strong base, like NaOH, and heat. The OA takes the proton from NHU, releasing NHAs. NaCl plus NaCl plus HCl plus NaHO.
Oxides of nitrogen, NO sources.
Naturally formed by lightning. High energy reaction of N-O. Man-made sources mainly from high temperatures in internal combustion engines.
How are they removed from car exhaust?
Catalytic converters use catalysts like PTRH to convert NO into NOA, reacting with CO, e.g. 2CO plus 2NO-A, 2CO plus N.
Do they contribute to smog?
Yes. In sunlight, nodrax react with unburned hydrocarbons to form photochemical smog, which includes harmful compounds like PAN, peroxyacetyl nitrate,
And acid rain?
Yes. Nodrax reacts with water to form nitric acid, HNO. Also, nodrax catalytically oxidize SO in the atmosphere to SO, which then forms sulfuric acid, HNO. Both HNO and HOs contribute to acid rain.
Okay, final stretch. Intro to AS level organic chemistry. 13.1, 13.4. Basic definitions, hydrocarbon, functional group.
Hydrocarbon, compound of only carbon and hydrogen. Alkanes are the simplest, saturated, no functional group. Functional group, specific atom group of atoms determining chemical properties, for example, nanoros for alcohols, CC for alkanes.
Formulas. General structural displayed
General, e.g. CnH2n plus 2. Structural shows connectivity, like CACHRS. Displayed shows all atoms, all bonds. Skeletal lines for CC bonds, C atoms of verticence, H on C omitted, functional group shown.
Naming, IUPAC.
Systematic naming rules, IUTAC, based on longest carbon chain, functional group position, side chains. Need to name draw structures for simple alkanes, alkenes, halogenyl alkanes, alcohols, aldehydes, ketones, carboxylic acids, esters, amines, nitriles. Up to 6 carbons usually.
Molecular versus empirical formulas from structures.
Easy. Molecular dot count actual atoms. Empirical, find simplest whole number ratio.
Key reaction terms, 13.2. Homologous series, saturated and saturated.
Homologous series. Same functional group, general formula, similar chemistry, differ by CHs, alkanes. Saturated only CZ, single bonds. Unsaturated contains CC or SPACFs.
Shapes of organic molecules with 13.3 hybridization.
There's
branch to SPS.
Your shape around carbon depends on bonding. SPL 4 single bonds, tetrahedral, 109.5 degrees. SPSAC, triple bond linear, 180 degrees. Sigma, single bond, direct orbital overlap. Pi bonds, sideways people overlap. Double bond equals 1 plus 2. Pi bonds restrict rotation.
Planarity.
Atoms around in 6 carbon, like in ethene CC, lie in the same plane.
Isomerism.
13.42.
0.42. Structural versus stereosomerism.
Isomers. Same molecular formula, different structure. Structural isomerism. Different connectivity. Types.
Chain.
Different C skeleton. Positional, functional group in different position. Functional group, different functional group. Ethyl alcohol versus ether.
Stereosomerism.
Same connectivity, different spatial arrangement types. Geometrical. Cis strands, or EZ, in alkenes due to restricted rotation around CC. Optical, in enantiomers, non-superimposable mirror images.
What causes geometrical isomerism?
Restricted rotation around the CC double bond, and each carbon in the double bond must be attached to 2 different curves.
What causes optical isomerism?
A chiral center, usually a carbon atom bonded to 4 different groups, leads to 2 non-superimposable mirror image molecules and enantiomers. Need to identify chiral centers and geometrical isomerism in structures.
Let's touch on specific hydrocarbon types. Alkanes, 14.1. Production. Reactions.
Production, hydrogenation of alkanes, H-ion catalyst, cracking of larger alkenes. Reactions, combustion, complete CoO plus HCO, incomplete COC plus HOO, free radical substitution with clue HO less pitch, HE plus HCl.
Environmental issues with alkanes.
Incomplete combustion produces toxic CO. Engines produce NOx, smog, acid rain precursor, by catalytic converters.
Alkanes, 14.2. Production. Reactions.
Production, elimination from halogenyl alkenes, hydrogen alcohol, dehydration of alcohols, allergens, exogen or dehalogenyl alkane.
Electrophilic addition of alkanes.
Cold dilute acidified KMNO E-diol, adds SOH across double bond. Hot concentrated acidified KMNO ERO breaks C-key-C bond, forms ketones, aldehydes, carboxylic acids, or co-aros depending on substitution pattern.
Carbocation stability. Markovnikov's rule.
During electrophilic addition, e.g. with HBr, and intermediate carbocation forms, stability. Tertiary, 3 R groups on C. Secondary, 2 R groups. Primary, 1 R group. Markovnikov's rule states the H atom adds to the carbon of the CC that already has more H atoms because this forms the more stable carbocation intermediate.
Halogen compounds, 15.1. Production of halogen alkanes.
Free radical sub of alkenes. Electrophilic add of HXX to alkenes. Substitution of alcohols using HX, PCLEs, PCLEO, SOCl.
Classification. Primary, secondary, tertiary.
Based on the carbon the halogen is attached to, primary C attached to 1 other C. Secondary C attached to 2 other Cs. Tertiary C attached to 3 other Cs.
Key reactions. Nucleophilic substitution.
Halogenyl alkenes react with nucleophiles, species with lone pair negative charge. With NOHHO, heat alcohol, OH replaces X. With KC-nethanol heat, NH-triol, CN replaces X. With NHHE ethyl heat pressure amine, NHE replaces X.
Reactivity differences. CX bond strength.
Reactivity depends on mechanism, SN1, SN2, and CX bond strength.
Yeah.
CI bond is weakest, CF strongest. So idoalkenes react fastest, fluoroalkenes slowest in substitution. Tertiary often react faster via SN1, primary faster via SN2. Test reactivity by warming with aqueous silver nitrate faster precipitate, AgX, means more reactive halogenyl alkane, AgI forms fastest.
Hydroxy compounds alcohol, 16.1. Production methods.
Hydration of alkanes, ethene LO eros. Oxidation of alkanes, cold KM in orals.
Oh.
Sub of halogenyl alkanes, NaOHE. Reduction of aldehydes ketones, nebicelal, urosoli secondary alcohols. Reduction of carboxylic acids, linolase are primary alcohols. Hydrolysis of esters, acid alkali.
Reactions of alcohols. Combustion. Substitution.
Combustion euro plus H-euro. Substitution to form halogenyl alkanes with HX, PCLs, PCl, SO keros. Reaction with sodium metal, S-sodium alkoxide plus H-air gas.
Oxidation. Dehydration.
Esterification.
Oxidation, acidified K-CuRO x E2N by 820 by 87 KMnOO. Primary alcohols, aldehydes distill off, or carboxylic acids, reflux. Secondary alcohols, ketones distill off. Tertiary alcohols, no reaction. Dehydration, heated aleoconc alkanase. Esterification, react with carboxylic acid conc. H is O catalyst, ADO plus water.
Carbonyl compounds, aldehydes and ketones, 17.1.
Production. Oxidation of primary alcohols, distill aldehydes. Oxidation of secondary alcohol, distill ketones.
Reduction, nucleophilic addition.
Reduction, NABLALEO, aldehydes, H alcohols, ketones, secondary alcohols. Nucleophilic addition of HCN, KCN catalyst, hydroxynitriles, cyanohydrins.
Esters, 18.2. Production, hydrolysis. Production, esterification, alcohol plus carboxylic acid plus conjugate. Hydrolysis, breaking ester bond. Acid hydrolysis, dilute acetate reversible, carboxylic acid plus alcohol. Alkaline hydrolysis, dilute alkali heat, reversible, carboxylate salt plus alcohol.
Nitrogen compounds. Amines and nitriles, 19.1, 19.2. Amine production.
Primary amines from halogenocanes plus excess NH-ethanol heat pressure.
Nitrile production. Hydroxynitrile production.
Nitriles from halogenocanes plus casein ethanol heat. Hydroxynitriles from aldehyde ketones plus HEN KCN catalyst.
Nitrile hydrolysis.
Hydrolysis with dilute acid or alkali, followed by acidification if alkali used, hot carboxylic acids. The SCAS N group becomes NaCeAOH.
Polymerization. 20.1. Addition polymerization.
Monomers, small molecules, usually alkenes, add together to form a long polymer chain without losing any atoms. Example, ethene polyene, chloroethene poly, so ethene, PVC, requires breaking the bond in the monomer.
Can we deduce repeat units or monomers from structures?
Yes. The repeat unit is the section derived from one monomer molecule. Given a polymer section, you can identify the repeat unit and thus the original monomer by putting the double bond back in.
Disposal issues with polyalkenes.
They are generally non-biodegradable due to strong CCCH bonds. Burning can release toxic gases, for example, HCl from PVC. Recycling is important, but can be difficult.
Organic synthesis, 21.1. Putting it all together.
Yes. Identifying functional groups in complex molecules using known reactions. Predicting properties. Devising multi-step synthetic routes to make a target molecule using reactions from the syllabus. Analyzing given synthetic routes, reagents, conditions, byproducts.
Finally, analytical techniques. 22.1, 22.2. Infrared IR spectroscopy.
Used to identify functional groups. Different bonds absorb IR radiation at characteristic frequencies wave numbers, causing them to vibrate. An IR spectrum shows these absorptions, troughs. Use a data table to match absorption peaks to specific bonds functional groups, like OH, COCH.
Mass spectrometry.
Used to find molecular mass and get structural information. Molecules are ionized, often losing one electron to form matte. Ions are separated by mass-to-charge Me ratio. The peak with the highest Me is usually the molecular ion peak, MAP, giving the molecular mass. Lower Me peaks are from fragmentation of the mass ion. The fragmentation pattern gives clues about the structure, can also determine isotopic abundance, and calculate relative atomic mass.
Wow, that was comprehensive. We've covered an immense amount of AS-level chemistry.
We certainly have. From the structure of the atom right through to making and identifying organic molecules.
And hopefully you can see how it all connects. Atomic structure influences bonding. Bonding dictates structure and properties, which determines reactivity, energy changes, equilibrium.
It's all logical, step by step. Understanding these fundamentals really does provide a solid base for further study or just understanding the world.
Definitely. It's not just for exams, it's the language used to describe how matter behaves. So, our final thought for you.
Yeah, maybe consider how these principles we've just skimmed across are playing out everywhere. From, I don't know, how a battery works, to why certain materials are strong, to the processes happening in the atmosphere. Chemistry is literally the foundation of everything. Keep looking, keep wondering.